Alright, welcome back everyone. So today we're going to be continuing linear algebra done right, the second chapter. Namely, we're going to be discussing finite dimensional vector fields. We'll get to that definition later, and also infinite dimensional vector fields, but for now, we're going to be introducing the concepts of span and linear independence. This is the first section in the book, and these are two key concepts to master. And so, we all remember what linear combinations were. Well, if we have a set of n vectors in a vector space V, alright, then we define a linear combination of those two vectors where to be the product here, a1 v1 plus all the way to an vn. That is a linear combination of these a set of n vectors where a1 through an are in some field f. Okay, so that's a linear combination. Just a quick review. And now this brings us to the definition of span. What if we take the span of n vectors in a vector space? Well, by definition, this is technically a definition, but definition is span. So the span, we say the span of n vectors, denoted as such, is equal to the set of all linear combinations of those n vectors. So I'll just say a1 v1 plus all the way through an vn, such that a1 through an are, again, in a field f. That is the definition of span. Okay, and this leads us to the question, what do we call a space that is, what do we call this resulting set that is, sometimes the span of vectors, as we've seen, produces an interesting set. And so that set is called, if a set is spanned by a set of vectors, that set is said to be spanned by that set of vectors. And so, or in other words, these vectors span this set. Okay? For example, well, we'll get to basis later, but of course if we have, and actually these vectors are then called a spanning list for that vector space. Before we talk though, before we discuss more on this, we need to show that the span is in fact a subspace. Okay, the span is a subspace of the vector space V, and so it's just another way of saying that it's again a vector space but a subset of V. So I use that term vector space loosely because we haven't proved that yet, but we will prove that. Okay, well, before we get to that, let's quickly, since this is the name of the chapter, let's quickly see what a finite dimensional vector field is. A finite dimensional vector field is a vector field which can be spanned by a finite number of vectors. Is spanned by a finite number of vectors. Okay. So once we prove that the span is a vector field, this resulting set is a finite dimensional vector field because it's spanned by a finite number of vectors. That's a finite dimensional vector field. An infinite dimensional vector field is one that is not finite dimensional vector. It cannot be spanned by a finite number of vectors. Therefore, an infinite number of vectors. Okay, and we'll get to an example of that once we prove the span is indeed a subspace of V. Well, let's see. And it's in fact the smallest subspace containing these n vectors. We'll have to prove that. So, one, it's a subspace. That's not too hard. The identity is there. Why is the identity there? Well, clearly, Again, here's our definition. Clearly, a vector, we can set all AIs equal to, so every AI equal to 0, which is in the field, the identity element, and so 0 v1 plus dot 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 0 vn. We know we've actually shown this to be just 0, okay? And, okay, let's see what else. Well, secondly, we have to show that if we sum two of these elements, it's another element in the set. Well, that's not too hard either. If we take another element, we can say a1 prime, etc. Then if we take the sum of those elements and regroup the elements, it's easy to show that we're going to have a1 plus a1 prime v1 plus dot 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 an plus an prime vn. Okay. Now clearly, a1 plus a1 prime is still a member of the field, etc. And so this is still in the span, in our span. I'm not going to write out everything. Okay. Well, that's nice. And scalar multiplication is analogous. Scalar times constants is these scalars is still a scalar in F in the field, and so it's in general it's still in the a member of the span of these vectors. Okay. Secondly, well, are these vectors in the span? Again, and you should notice that we're using a kind of similar technique to when we showed that the sum of subspaces is the smallest subspace containing those subspaces. It's the same sort of proof. Okay. Well, again, set AI equal to 1 and everything else equal to 0. So we have 0 plus 1. Well, so and then aj equals 0, I not equal to j. Okay. And so that will simply leave us with the vi element. Clearly this is, since all of these ai and ajs are indeed in our field, surely all of the vi's are in the field. And so, well, in the span, I should say. And so that's a check mark as well, because we can just run through all of the i's. Okay. And finally, we need to prove that it's the smallest. It's the smallest subspace containing these vectors. Well, remember that a subspace needs to be closed under addition and multiplication. And so if we have a subspace T, it's more like funny topology thing. Fancy tau. Anyway, if let's see, let's write it. If we have v1 all the way to vn is in the subspace T, well, since it's a subspace, it must be closed under addition and multiplication, and so it must contain all the linear combinations of these vectors, right? Because, well, for example, a1 v1 should be in the subspace. a1 v1 plus another constant times a vector which is in the subspace should be in the subspace, etc. And so that implies that this span of these vectors must be a subset of T. Again, by similar reasoning, this is QED. All right, good. Since this implies that if we take any subspace containing these vectors, it must at least contain the span. Okay. So we define finite dimensional vector field. Let me define it again. I'll write it out. So we say V is now in fact I'll abbreviate it, finite dimensional FD if it is spanned by finitely many vectors. An example of such a vector field, this is an important definition. An example of such a vector field is Rn, for example Rn, where n is a finite number, it's not infinity. R infinity would quite obviously wouldn't be finite dimensional, right? But we'll get to that. So Rn examples. Rn, you've surely heard of basis, which we'll go into more later on, but clearly we can use the standard basis for Rn, which spans Rn, right? Okay. How are we doing time-wise? I always look at the clock when it's like 11 or 12 minutes in. Okay, but we're more interested in finite dimensional vector fields, but it's always good to look at counterexamples. What if every vector field is finite dimensional? Otherwise, if this was the case, this definition would be useless. And so, infinite. So we look at infinite dimensional vector fields real quick. There's one example which I would like to cover. There's another example. I'm trying to think of the notation it uses. It's the set of all sequences. The set of all infinite sequences. The set of all sequences. That's infinite dimensional, quite obviously. But the more interesting example is the set of all polynomials on a field F. And again, infinite dimensional is if it can't be spanned by finitely many vectors. I explained that, but so the set of all polynomials on a field F, and we define that as the set of all polynomials taking z equals a1, c, z, well, I'll write it like this, a naught, this is how the book writes it, z plus dot dot dot. Well, this isn't quite what I'm looking for. Maybe what we can do, yeah, I'll write it like this. I'll write it as a union of an infinite number of subsets here. And the notation here, I believe, how does he write the notation? Yeah, that's what I expected. Union. Actually, this is not quite what we're looking for, because there's an important definition. In fact, before we define that general set, let's define, we give it another example of finite dimensional vector field, and that's a set of all polynomials of degree at most n. Okay, so this is a set of all polynomials, a0, this is quite big, a1z p plus dot 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 plus m z to the m. So set of all polynomials of degree less than or equal to m, such that ai for all ai is in field F, right? So that's what we're looking at. This is clearly finite dimensional. In fact, we can say it's in this vector space. We can look at a spanning set which consists of all monomials of degree up until m. So we can say that this is equal to the span of 1z up until zm, right? Because, I mean, in our vector, this is literally the definition. We're looking at all linear combinations of these vectors, of these quantities in our vector space, which is, in fact, the following. This here, okay? All monomials up until m. So now we're ready to look at this infinite dimensional vector space. Set of all polynomials of any degree, and in fact this is spanned by infinitely many vectors. Of course this generalizes to, but this goes on till infinity. Alright, infinitely many vectors, okay? And so it's infinitely dimensional. Now, a better, more concrete argument to say that it's not finitely dimensional is that suppose, by way of contradiction, it was finitely dimensional, that we can write the span as the following. Finite number, well, to be less vague, all the way to un. Well, let's see, one of these, so all of these, of course, are polynomials. They're inside of this vector space. And so they have to have some degree. Now we take the element with the largest degree, say that's uj, there surely exists such an element, and consider the degree of uj plus 1. Well, clearly that degree does not exist in the span, and so in other words this vector space cannot be spanned by a finitely many set of vectors, right? So that's one good example. Okay. Let's see. Yeah, so we define degree, infinite dimensional vector field. Perfect. Okay, and now we are ready for linear independence and dependence. Alright. So that means we are free to erase this. Linear independence and dependence, okay. So there are a few ways of doing this. Well, I'm sure you're already familiar of definitions of linear independence and dependence from, introductory linear algebra. So I guess we need some motivation. If we look at two unique linear combinations of n vectors, a1, b1, all the way to an, bn, equaling some vector in a vector space. So we're working in this vector space V, see a1 prime, b1, an prime, bn equals V. we subtract these, notice the similarities between this and subspaces, operations we've done with subspaces. An prime equals 0. Now we're interested in subspace. We're interested in sets of vectors such that the only way this can equal 0 is if a1 and a1 prime, etc., all down the line, are equal to 0. That is the trivial solution to this. That is a1 equals a1 prime. Hence, every vector can be expressed uniquely as a linear combination of vectors. And so those types of vector fields are, those types of sets of vectors are called linearly independent sets of vectors. Okay? So we say v1 all the way through vn and v are linearly independent if a1 v1 plus ... an vn equaling 0 implies that each ai is equal to 0. Okay. Well, that's important. I think, well, let's quickly define linear dependence. We're running above 22 minutes again, which is where I kind of want to stick. So linear dependence, a linear dependent set of vectors is one that is not linear independent. More specifically, it is a vector. It is a set of vectors such that there exists a non-zero coefficient here, such that this linear combination equals 0. Conversely, are lin dependent if there exists, let's call it aj in our field, aj non-zero, such that I guess we should say with aj non-zero. I guess it's more compact to write. It's by assumption in our field exists aj non-zero such that a1 v1 plus ... aj vj plus ... plus an vn equals 0. So there exists at least one coefficient a such that this holds. And so we'll continue here and prove important results about linear independence and dependence. See you then.